Okay, for a second, I want you to forget everything you might remember from that high school math class. We're not here to talk about a bunch of dry equations. We're here to talk about a language. A truly profound language that was designed to describe a universe that is in constant, beautiful motion. So let's dive in and explore this amazing language of becoming. This quote just nails it, doesn't it? It perfectly captures the whole idea. We're shifting gears from the simple yes or no, the on or off of Boolean logic, and we're stepping into the fluid, continuous reality of becoming. You know, how things actually grow and move and transform in the real world. Calculus is literally the formal study of how change itself behaves.
So here's our game plan for this journey. First up, we'll meet the incredible minds who forged these tools. Then, we're going to learn how to take a snapshot of a single, fleeting instant. After that, we'll see how to build the entire picture back up from all those tiny pieces. And finally, we'll get into how calculus helps us find the absolute best path through almost any problem you can imagine.
You know, for centuries, mathematics was absolutely brilliant at describing things that were static, things that just sat still. You know, the angles of a triangle, the area of a circle. But the real world? It doesn't do that. It flows, it accelerates, it evolves constantly. And for a long time, math just didn't have the vocabulary for that. I mean, really think about that for a second. The speed of a thrown ball is different at every single moment of its flight. A plant isn't just growing, its rate of growth is always changing, minute by minute. So how do you pin down a number to describe something that just refuses to be pinned down? This was the fundamental challenge that had mathematicians stumped. Well, the answer to that massive challenge came from two of the greatest minds of the 17th century. And what's wild is that they were working completely independently, but they both forged the tools for this powerful new language. So let's meet the architects of calculus, Isaac Newton and Gottfried Leibniz. And what's so fascinating here is that they got to the same place from two totally different directions. Newton, ever the physicist, saw calculus as a way to describe physical motion through time. He called it the method of fluxions. But Leibniz, the philosopher, he saw it as creating this perfect, elegant, symbolic language to express the very idea of continuous change. So you have two unique perspectives, but they led to one revolutionary toolset. And this is the keystone. This is what holds the entire structure of calculus together. The fundamental theorem of calculus revealed this absolutely breathtaking secret, that breaking things down to analyze them and summing things up to rebuild them were perfect mirror images of each other. They're inverse processes. It's this beautiful, inseparable duality of analysis and synthesis. All right, let's start with the first part of that duality, analysis. This is differentiation. This is the tool that lets us zoom in on a single, infinitesimal moment in time to understand exactly what is happening right then and there. Your speedometer does this all the time, right? It doesn't tell you your average speed over the last 5 minutes. It tells you your speed right now. But think about it. What even is right now? It has no duration. It's a single point in time. That's the exact paradox that calculus was invented to solve. And the answer to that paradox is the derivative. A derivative is the mathematical tool that lets us find that instantaneous rate of change. It's the grammar of motion, giving us the precise velocity of that car or the exact growth rate of that plant at one specific single point. So how does it actually work? Well, it's a really clever trick. Imagine you're on a winding, curvy road. If you want to understand the road's exact direction at one specific spot, all you have to do is look at the straight line, the tangent line, that just kind of kisses the curve at that one point. A derivative gives us the slope of that line. It's a brilliant way to understand complex curvature by looking at something perfectly simple and straight, even if it's just for an instant. And that's really the power of the derivative. It gives you this moment of absolute clarity, a momentary truth about how a system is behaving, capturing its entire essence in a single frozen instant. Okay, so now let's flip to the other side of that coin. If derivatives are all about breaking things down into tiny little instants, integration is about building them back up. This is synthesis, the incredible art of summing up an infinity of tiny pieces to understand the magnificent whole. And the tool we use for this is the integral. You can think of it as a master of accumulation. It's what answers questions like, if your speedometer logged your speed every single instant of a long road trip, how could you figure out the total distance you traveled? Well, integration reconstructs that entire journey from an infinite number of those little momentary snapshots. So here's how that process works. Let's say we start with a complex, curvy shape that's really hard to measure directly. What we do is we slice it into an infinite number of incredibly thin rectangles, which, are super easy to measure. Then integration acts like this sort of super adder, summing up the areas of all those tiny little slices. And the result? A perfectly precise measurement of that original complicated shape. It's literally synthesis from fragmentation. So we can break things down and we can build them back up. That's cool. But where calculus becomes truly mind-blowingly powerful is when we use these tools to find the best possible answer, the maximum height, the minimum cost, the most efficient path. This is optimization, and it basically runs our modern world.
Right at the heart of optimization is this idea called the gradient. So imagine you're on a massive mountainside, but you're in a thick fog, and you're trying to get to the very top. The gradient is like a magical compass at your feet that always points in the direction of the steepest path up. If you just keep following that compass, you are guaranteed to find the summit in the most efficient way possible.
And this geometry of optimization is absolutely everywhere. It's used for everything from calculating a rocket's trajectory to modeling financial markets. And get this, it's also how artificial intelligence learns. Think of an AI's error as this huge, foggy landscape of mountains and valleys. Every time it makes a mistake, the gradient is the compass that tells it which direction is downhill, toward a smaller error. So by taking millions of tiny steps downhill, it eventually finds the valley of correctness, and it learns to get the right answer. So let's zoom out one last time. When you put all these incredible pieces together, the derivatives, the integrals, the gradients, you get something much bigger than just a set of mathematical tools. You really do get a new way of seeing the world. It turns out, calculus is the grammar of change. It's the language that allows us to write the story of the universe, from the orbit of a planet all the way down to the firing of a single neuron. It reveals the underlying rules that govern how everything, from a physical system to an economic market, evolves over time. So, I guess I'll just leave you with this thought. For over 300 years, calculus has been our main language for understanding a dynamic world. But today, our world is changing faster and in more complex ways than ever before. So what comes next? What will be the grammar of the next scientific revolution?